Hello, I welcome you all to your own channel MSK Learnium. In this video, we are going to discuss about the Otto cycles. So Otto cycle is an air standard cycle which works on constant volume. Means the heat addition and heat rejection will be at constant volume and adiabatic compression and the adiabatic expansions. So the cycle is invented in 1876 by a German engineer. Name is the Nicholas A. Otto. So that's why we give the name is the Otto cycles. Right now, so Otto cycle you can write it is an air standard SI engine. It is an air standard SI engine. SI engine means spark ignition engine. Spark ignition means what? That a spark plug is used for ignitions, or you can say that it is the petrol engines. Right now, so this Otto cycle is having four processes. So you can say the Otto cycle has four processes, right? Has a four thermodynamic processes. Okay, so what are the four thermodynamic process? We will see. First of all, you have we can write here itself, that is 1 to 2 adiabatic compression, that is reversible adiabatic compression. Right, reversible adiabatic compressions. After compression, you have to supply the heat. How we are supplying the heat? By keeping volume constant. So next process you have a 2 to 3, that is constant volume heat supplied. Okay, next after adding the heat, you have to expand this. Means what? That next you can say the 3 to 4 is the reversible adiabatic expansion. Next you have a 4 to 1, that is heat rejection at constant volume. So 4 to 1 constant volume heat rejection. Alright, heat rejection. So these are the four processes which will be executed in an Otto cycle, or you can say the air standard SI engines. That is 1 to 2 reversible adiabatic compression, 2 to 3 constant volume heat supplied, 3 to 4 adiabatic expansion, 4 to 1 constant volume heat rejection. As you know that 4-stroke IC engines means 4-stroke SI engine process is what? That suction, compression, expansion and exhaust. So first of all, in compression, that we have to compress the fluid. How the compression takes place? Adiabatically. Again you have to supply the heat by means of the spark plug. The heat is generated, means combustion will take place, then that is constant volume. Again expansion in expansion stroke, and finally heat is rejected through the exhaust valve. Right. So now this process we will see on the PV and TS diagram, which is the very important for you to understand the thermodynamics cycles. Right. So first of all, we will draw the pressure versus volume diagram for the Otto cycles. So here we go, that PV diagram we are going to discuss. For that we will take pressure on y-axis and the volume on the x-axis. Right. So first we have a that is adiabatic compression. So you can say, let's say this is your adiabatic compression, and 2 to 3 heat supplied at a constant. This is 1 to 2, that is adiabatic compression. Arrow is up, right? And then 2 to 3 heat is supplied at constant volume, right? And again 3 to 4, that is adiabatic expansion. This is 3 to 4 adiabatic expansion, and 4 to 1 we have a heat is rejected. So 1 to 2 adiabatic compression, 2 to 3 constant volume heat supplied, 3 to 4 adiabatic expansion, and 4 to 1 heat rejection at constant volume. Right. So now you can see here, that is we are adding the heat and here we are rejecting the heat. Right. So these processes are the constant adiabatic. So adiabatic law is followed, that is PV to the power of gamma is equal to constant. Right. Now, so first of all is what? That at the point 1, pressure, volume and temperature will be P1, V1, T1. When compression takes place, the pressure and temperature will increase but the volume will decrease. And again at constant volume, heat will be supplied, temperature and pressure will rise. And 3 to 4, that the pressure is decreasing and temperature will also decrease, but the volume will increase. Again, at constant volume, that heat will be rejected. So this is what you have a pressure versus volume diagram for the Otto cycle. If we see that temperature versus entropy diagram for the Otto cycle, so how it will be? So here we go, that the temperature I am taking on y-axis and entropy will take on the x-axis, right? So here is the temperature and this is the entropy. So as the first of all, you have a two constant volume line you have to draw, right? So let's say I am drawing the two constant volume line. So this is the heat supplied line and this is the heat rejection, right? So here 1 to 2 is the adiabatic compression. So 1 to 2, right? When the compression will take place, the pressure, temperature will rise, but the volume will decrease, right? Again, you have a 2 to 3, that at constant volume heat will be supplied, right? So heat will be supplied from 2 to 3, that is constant volume, and again after supplying the heat we have to expand this, that at constant adiabatically 3 to 4 reversible adiabatic, and 4 to 1, that is heat is rejected. So this is what now you can see here, that you can show this is your heat supplied, that you can say QS, and this is the heat is rejected, which is QR, right? So here you have a compression, expansion, heat supplied and heat rejection. This is the volume is constant. There is also volume is constant, and PV to the power gamma is constant, and PV to the power gamma is constant. Now we will see the efficiency of a Otto cycles, that is air standard efficiency of Otto cycle we will see right now. So now next we can go for the air standard efficiency of Otto cycle. So let's do that also. Okay, so here you have a, first of all you can write subheading, that is air standard efficiency of Otto cycle. Air standard efficiency of Otto cycle, right, of Otto cycle. So this either Otto cycle, diesel cycle or dual combustion cycle, these all are in the one phase only, and the working fluid will use as a air, right? So that's why the air is standard efficiency and the phase is not changed. Means what? When you are doing the compression 1 to 2, it is gas, 2 to 3 gas, 3 to 4 gas only, and 4 to 1 gases only. But if you look at that Rankine cycle, right, which is used in the steam power plant, in that the phase is changes from liquid to vapor and vapor to liquid. But in Otto cycle the phase does not change, it is in the gaseous state only, or the working fluid is the air, right? So here we'll go the efficiency of air standard efficiency. So we can say efficiency of Otto cycle, that is neta Otto, is equal to output by input, right? So output is what? That output is nothing but you can say work done, WD is the work done, and the input is the heat supplied. Again you know that work done is equal to what? Work done is equal to heat supplied minus heat rejection. Okay, so when you substitute this into the above equation, the equation efficiency of Otto cycle will become heat supplied minus heat rejection by heat supplied. This value we are substituting here, right? So the equation will become heat supplied get cancelled. So Otto efficiency is what? That is neta Otto is equal to 1 minus heat rejection by heat supplied. Let's find out the heat rejection and heat supplied from the PV or TS diagram. Any diagram you can follow. I am taking this PV. That is 2 to 3 we are supplying the heat at what? Constant volume. And whatever the working fluid is circulating in a cycle, that we will consider the 1 kilogram. Means what? Mass of the air is 1. So you can write for better understanding, for 1 kilogram of air, right? 1 kilogram of air means wherever we'll find out the heat supplied, heat rejection, mass is multiplied actually, but because of 1 kilogram, the value magnitude is 1 kilogram, we need not to show, right? So heat supplied is what? That you can say heat supplied, that is QS is equal to, you are supplying the heat from 2 to 3, right? From 2 to 3. So what? MCV T3 minus T2, right now. So you can write it here, that is mass into CV, that specific heat at constant volume, into T3 minus T2. As I consider the mass is 1 kilogram, so this equation will become CV into T3 minus T2, Alright. Similarly, we can go for the heat rejection, that is QR is equal to what? The same, but from the 4 to 1 process. 4 to 1 you are rejecting the heat at constant volume itself. So it will become, that is mCV T4 minus T1, right, is equal to CV T4 minus T1. Okay, these value we will substitute into this equation. The equation will become like this, that is neta Otto is equal to, you can see here that neta Otto is equal to 1 minus CV T4 minus T1 by CV T3 minus T2. CV get cancelled. So efficiency of Otto is what? That efficiency of Otto is nothing but 1 minus T4 minus T1 by T3 minus T2. Let's say this is equation 1. Now come back to the compression and expansion process. Compression and expansion is we are taking adiabatically, means 1 to 2 and 3 to 4. 1 to 2 is the compression, adiabatic, and 3 to 4 is expansion. We will get the relation between temperature and volume, right? So here you can say that 1 to 2 process, right? 1 to 2 process is what? That you can say T2 by T1 is equal to V1 by V2. This is the thermodynamic relation, you know, by to the power gamma minus 1. And the V1 by V2 is nothing but the compression ratio, right? So compression ratio we are denoting by RC. So this T2 is equal to T1 times of RC to the power gamma minus 1, right? So here you can write where RC is equal to V1 by V2, that is compression ratio, right? Compression ratio. Okay, now so RC is the compression ratio and it is the value is what? V1 by V2. One relation we got for T2, right? T2 is equal to T1 times of RC to the power gamma minus 1, you can say. Now we come to the expansion. Where is the expansion? That 3 to 4. So 3 to 4 process, you can say that 3 to 4 process, right? So 3 to 4 process is what? We can say here that T3 by T4 is equal to V4 by V3 to the power of gamma minus 1. But if you look at here, that this is what? This is your constant volume, V4 and V1, and the V3 is V2, that is constant volume. So V4 is equal to V1 and V3 is equal to V2. Why? Because it is constant. So this equation will become V4 by V3, you can say V1 by V2, right? So here we can write, or we can change the next page, right? And then I'll show you. Right. So now we can say that since V1 is equal to V4 and V3 is equal to V2, right? So whatever the relation you got, what? That is, what your relation you got? That T3 by T4, right now. So T3 by T4 is equal to V4 by V3, again I am writing to the power gamma minus 1. That is nothing but V1 by V2 to the power of gamma minus 1. And V1 by V2 is what? RC, that is compression ratio. So you can say T3 is equal to T4 times of RC to the power gamma minus 1, right? What is the equation 1? The equation 1 we got, that is 1 minus T4 minus T1 by T3 minus T2, right? So you can say from equation 1, right? What is that? Efficiency of Otto is equal to 1 minus T4 minus T1 by T3 minus T2. Alright. So here 1 minus T4 minus T1 will leave it as it is. So T4 minus T1, T3 is equal to, you can substitute T4, sorry, this is RC, right? T4 times of RC to the power gamma minus 1, and again T2 is equal to T1 times of RC to the power gamma minus 1, right? So here RC to the power gamma minus 1 will get common. So this equation will become 1 minus T4 minus T1 by Rc to the power gamma minus 1, and the remaining is what? T4 minus T1. So this T4 minus T1 and this T4 minus T1 get cancelled. So when it is cancelled, the equation will become like this. That is, efficiency of Otto cycle is equal to 1 minus 1 by Rc to the power gamma minus 1. Right? So this is what you have a efficiency of a Otto cycle. It means that you can say the efficiency of a Otto cycle or air standard IC SI engine or the petrol engine is totally depends on the compression ratio, right? So for a compression ratio is what? If the compression ratio value will be high, the efficiency is also high. Is it or not? So that you can conclude here that the efficiency of Otto is function of what? Compression ratio, right? So you can say for higher compression ratio, right, the efficiency of air standard SI engine is high, will be higher, right? Or Otto cycle efficiency is higher. So this is all about the Otto cycle. In next video we will see the diesel dual combustion Stirling Lenoir cycle. Thank you.